This is our fourth of our coordinate transformation videos. We're on number 4. We're just going to tie up a few loose ends and try to summarize a little bit and talk about scaling also in this one. So we had essentially two different ways to do our matrix transformations. If all the transformations were with respect to new relative coordinate systems, we handled things one way. If all the transformations were with respect to the original machine or model coordinate system without intermediate coordinate systems or any working coordinate system really, then we handle it a different way. So on the notes here, I've got the first method, let me go up here. The first method where we have kind of relative translations and relative rotations, because each time it's about the new coordinate axis. Actually, this one should say about the new x, and then rotated about the new y. And you see here the sequence t, rx, ry shows up in the equation in the order that it happens. So the working coordinate system, first it's translated, then it's rotated about y. And the multiplication itself, or we can think about the vector here as first being multiplied by the last step, and then the result there being multiplied by the intermediate step, and then that result being multiplied by the original step. And then that way it kind of brings the vector one by one back from the working coordinate system back to the model coordinate system. But again, the sequence in the equation is from left to right in the order that it happens. Now the other approach is when we have all of the transformations just with respect to the machine coordinate system or the model coordinate system. So we don't move relative each time. It's more what we call an absolute transformation. So in this case, for example, if we've got some element like a point, and first it gets translated, then it gets rotated, and then it gets rotated again, all about the original vectors, then the sequence in the equation is reversed. Our y, our x, our t. And in this case we can think about, here's the point, or the vector that gets changed, and the first thing that happens to it is the translation, even though that was the first step in what happens. So it's here's the vector, first thing happens, it gets translated, then the result of that gets rotated about the 30 degrees about x, and then the result of that gets rotated the minus 20 about y. So in this sense, now we've got a vector that just keeps getting moved around, and yeah, the order of the operation on the vector in some sense goes from right to left, but the resulting equation as we write it shows kind of a reversed sequence. So first matrix here is the last thing that happens, the second matrix, and then the third matrix is the first thing that happens. So hopefully that's not too confusing. A little practice should get it cleared up. Now in either of those cases, we were solving for the MCS system based on some transformation or rotation, all that times the coordinate in the working coordinate system. So in both of those examples, we assumed we knew P sub W, and we just had to solve for the result P sub N. But if you remember from the first video, we can go the other way too. If we know P sub M, the coordinate in the global or the machine coordinate system, we can solve for the point in the working coordinate system by taking the inverse of that transformation. So if our transformation, actually the one above it, we had PM equals Ry, Rx, T times PW. If we want to solve for PW, it's Ry, Rx, T inverse times P sub N. So that inverse is something you could do on Excel or with a mathematical program. It's actually not as hard as it looks. we note there's actually a property in matrices where if we have any matrix A times any matrix B, if we take the inverse of the result, that's B inverse times A inverse. So the inverse of Ry Rxt is equal to T inverse Rx inverse Ry inverse. So here we reverse the order again just to do the computation. So it's a little confusing. We had a reversed order in the past based on the type of transformation we wanted. But now here you might end up reversing the order if we're trying to do the inverse of that matrix. And remember, if T was something like delta x, delta y, and delta z here in that last column, then see, T inverse is the same. We would just replace that last column with minus delta x, minus delta y, minus delta z. And also, if we have a rotational matrix, we can kind of do the same thing, that the inverse of that rotation matrix just replaces any place you see a theta, we replace it with minus theta. So for example, the cosines end up the same and the sines switch sign. So that's a simple way to get the inverse matrix of any of our rotations, either about x, y, or z. We should keep in mind that every time we said P, like up here we have the point in the MCS, or P the point in the WCS, we've defined it mostly for a point each time, a point vector. But it doesn't have to be. Really, it's any entity. It could be a line, a curve, a surface, a solid. For example, if P is a line, it might look something like this. Say 2u plus 7 minus 3u minus 1, 4u, and 1. And that defines a line segment, as long as u, the parameter, runs from one starting value to a finished value. For example, u might run from 0 to 1, and that would establish a whole set of points along a line trajectory, and that P defines then a segment from u equals 0 to u equals 1. So it's a line segment, and if we wanted to translate that, say with some translation matrix that looks like this, suppose we wanted it to shift by 2 in the x, and then 0 in the y, and 5 in the z. We could take that translation, multiply it by our line segment, and we get a result that would look like 2u plus 9, because we basically shift the x-coordinate over by 2. The y-coordinate doesn't change, and the z-coordinate gets shifted over by 5. So there's a new vector representation of a line segment that's been shifted by 2 in the x and 5 in the z. And so that works the same way as a point vector. So that's just something we'll see as we start defining lines and curves and solids and surfaces. The last thing we'll do is scaling. And scaling, we see a whole new matrix down here. And really I've defined the ability to scale differently in the x, the y, and the z direction. But if we were going to just scale uniformly and maybe double the size of our matrix or scale it by 2 in all directions, we could just multiply by this scaling matrix where a, b, c are all 2. So if we have 2, 2, and 2, we leave 1 the same, but that basically doubles the size in the x, y, and z direction for any element. To handle scaling, just like in any of the other translations or rotations, we do have to consider the order of the scaling. I'm going to do a real quick example on the board for this. So suppose that here's our coordinate system, x, y, z. And we've got a real simple vector. It's just 1, 1, 0. And so that's this vector with a point right there. 1 and 1. Let's think of what we can do to that point vector. We could shift by 2 in the x direction and then scale by 2 or double the size in new working coordinate system. So that's equivalent, basically, let's take a new coordinate system, shift it over by 2. There's our vector still in there. So that's delta x equals 2. And then scale it by 2. Take that whole thing, enlarge everything by a factor of 2. So that means we would take our initial vector, we'd need a shift by 2 transformation. Then we would want to scale 2, 2, 2, and then our entity, our element there, our 1, 1, 1, 1, 0, 1. So the first thing that happens to our vector, our 1, 1 vector, is it gets doubled to 2, 2, right? Because that's what we see relative to this new coordinate system. It's now 2 by 2. And then it gets multiplied and shifted by 2. So the result we get is essentially 4, 2. Now that's a little different than if we did anything shifted or scaled by the original coordinate system. Because here we've got basically an intermediate coordinate system after we shift by 2 and scaled in this new coordinate system. So we end up with 4, 2. Now let's suppose we shift and then scale by original MCS. So now what we're doing is relative to the original coordinate system. So remember, when we do anything relative to the original coordinate system, we do it in the opposite order. So here we'd start with the scaling. Then we do the shift. Multiplied by our vector. So in this case, the first thing that happens to our vector is it gets shifted by 2, and it becomes 3, 1, right? From 1, 1 to 3, 1. And then that gets scaled, everything gets multiplied by 2, and we get a result of 6, 2. So that's different than what we had the first time, which was 4, 2 as a result. So because we're doing it by the original coordinate system, we get a different result. Keep in mind that also, if we were to first scale it, scale by 2, then shift, also all with respect to the original coordinate system, we would reverse those. And we'd end up getting the same result as we had the other way, that we would first have the shift matrix, and then we'd have the scaling matrix, and it would first scale it up to 2 to 2, and then shift it over to 4 to 2. Okay, so that's our element, our 1, 1, that first gets scaled. So it's 1, 1, it gets scaled up to 2, 2, and then it gets shifted over to 4, 2. So the order that things happen is important, and you need to make sure you're putting them either in the forward direction or in the reverse direction in terms of multiplying those matrices. Okay? So we'll get more practice on these, and we'll see you soon.